in advanced thermodynamics, we're going to spend a lot of time talking about, the behavior of chemicals at the molecular scale and how these molecules arrange themselves within and throughout systems. In order to formalize our discussions, we're going to use, the language of combinatorics, or we're going to use tools from the mathematical field of combinatorics. And so, in general, if we're going to talk about, let's just kind of keep it general. In combinatorics, we're going to deal with permutations, right? And so a permutation is just the number of different ways that you could arrange a sequence of n objects. It's the number of different ways you can arrange a sequence of n objects. Okay? Alright, now the way we can arrange these objects depends on if the objects can be distinguished from one another. So if you just have a group of all balls that are all different colors, we would say that each of the balls are distinguishable from one another. And so in this case, if you have n number of distinguishable objects, right, and you're kind of lining them up all in a row, right, you got to line them up as like blue, red, green, or red, blue, green, right, or green, red, blue. There's different ways in which you can line them up. And so if we want to calculate the number of different ways we can line them up, what we would be calculating is the number of permutations, right? And so to calculate that, what we would be looking at would be the factorial of n, right? So this exclamation point is the factorial. So here, factorial would just be 1 times 2 times 3, so on and so forth, until you get to n minus 2 times n minus 1 times n. Okay? Alright, and so here, essentially what we're looking at is, we're looking at the product of a bunch of different outcomes here. So there's n number of ways of arranging it like this, or n minus 1 number of ways of arranging it like that. And so essentially, with this number of permutations, what we're calculating is the overall multiplicity of our system. Remember what we talked about in previous videos? Alright, and so we would abbreviate that or symbolize that by omega. Right? So with n distinguishable objects, our multiplicity is just the factorial of the number of distinguishable objects that we have. Okay? And one thing I want to point out, just as a reminder about how factorials work, is that by definition, the factorial of the number 0, we're going to say is equal to the number 1. Right? And so, here we were looking at the case where every single one of our objects is distinguishable from one another. So every ball has a different color. But now let's consider the case where that's not true, right? So let's consider the case that, in our set of n objects, in our set of n balls, that, 5 of the balls have the same color. So we have 5 red balls. So we would say n sub I number of our balls, or objects, are indistinguishable from one another. Right. But those 5 red balls are still distinguishable from the 3 blue balls that are in the set, or the 8 green balls. Right. So the n sub I are indistinguishable from one another, but distinguishable from the other t minus 1 categories of objects. Okay? And so in such a case, to calculate our multiplicity, we would do this. So our omega would have the n factorial, but then we would divide it by the number of objects that are in one category, factorial, and then the factorial of the number of objects that are in a second category, and then dot dot dot, we keep multiplying them, and then we divide it by the number of objects that are in the tth category. And so essentially what we're doing here, by dividing our n factorial by these things, is we're avoiding double counting. Right? Because, if we're dealing with, some number of indistinguishable red balls, if we switch one red ball for another, then the permutation is exactly the same, right? The system, the set, the arrangement of the balls in the row is unchanged. And so, by dividing the factorial by this, we're going to avoid double counting. To kind of make this a more tractable sort of example, let's think of the case where we just have two categories. So if there are only two categories, so our t is equal to 2, then our omega simplifies down to this. So omega is going to be our n factorial, and then we have the number of objects in the nth category, and because there's only two categories, the number of objects in that second category would just be big N minus little n. And we have the factorial there. Okay? Alright, so this is what omega would look like for the case where we just have two categories. Right? And this sort of calculation comes up quite a lot, that we actually have a shorthand abbreviation for it, where we have this open parenthesis big N over little n. Right? And this formula actually has a name. This is known as the binomial coefficient. Right, so you're talking about the permutations of two different categories. Okay? All right, to show you an example of this, let's consider the case where we're flipping a quarter. So if we flip a quarter 4 times, what we want to calculate is the number of sequences that have 3 heads. Okay? And so in this case, our number of objects, our big N, would be equal to 4. And in those number of flips, we want to find the number of flips that have heads, right? And that number of flips, there were 3 heads. Okay? So out of the 4 flips, we want to calculate the number of cases where 3 of those 4 involved a heads being face up. And so to calculate this, our omega, we would just use the binomial coefficient formula I defined earlier. Okay? So here we would take the factorial of 4, divided by the factorial of 3, and then here would be 4 minus 3 in that factorial. Right? So that's just 1. So in our omega calculation, in the numerator we have 4 times 3 times 2 times 1. In the denominator, we have 3 times 2 times 1, right? That's this factorial. This is this factorial. And then we're also multiplying it by the factorial of 1, which is just this. And as a result, we find that if we flip the quarter 4 times, the number of cases where we end up with 3 heads is exactly 4.